Week 16 of the TheMathsTutor.ie 30-week countdown for Leaving Cert Ordinary Level Maths. This week we're going to be looking at some more probability. So we're going to be looking at Bernoulli Trials and expected value and a couple of questions like that. As always, the full 30-week countdown is available for all full members on the TheMathsTutor.ie website, and there's loads of videos there to help you with your revision, and we always make a couple of videos available each week for people. So the first one here is 2017 paper 2 question 1, and this is a probability question that covers a few different topics. And the second video is from 2019 paper 2 question 3, and again this is going to be a probability question and it's going to have a Bernoulli trial in it. So we're going to see what Bernoulli trials are in a few minutes, but the first thing we're going to start with today are what is expected value and fairness. So when we're looking at expected value, we're looking at what value do we expect to get in something. So there is a formula for this, so we write it as EX. So we say expected value, EX, is equal to the sum of X times PX. So this can look a little bit daunting or a little bit unfamiliar. This thing here is a capital sigma, and it means the sum of, and that just means add together. So we're going to be adding together XPX. So what XPX means, these are touching, so this means we're going to be multiplying. X is my values, and they're being multiplied by the probability of that value. So we're going to be taking a list of values, we're going to be working out the probability of those values, we're going to multiply those two things by each other, and then we're going to add them together. Now the expected value is also the average. So another way of looking at it is an average outcome. So if I'm looking for an expected value, it's normally from a game or something that we can do, and it's going to say, so how much do you expect to win in this, or what is the expected value? And that's the same as the average outcome if you play that game repeatedly. So they're the same thing, so it's going to be the expected value. So you can have a game that has an expected payout of €1 or €2 or €3 and so on, and they're going to be our X, our values, and we multiply by the value, the probability. So what's the probability of getting a 1? What's the probability of getting a 2? What's the probability of getting a 3? And so on. And we add all those together. And your answer for E of X doesn't have to be one of the possible outcomes. So I was using an example there saying you could win €1 or €2 or €3, but you could work out with an expected value of €1.47. And that's absolutely fine. Just remember that if you're dealing with money, expected value, we would be rounding it to 2 decimal places for money. That's what our expected value actually is, but when we're looking at expected value, we also want to deal with fairness. So when we're talking about fairness in probability, it means that the expected value is equal to the cost. So if something is fair, the expected value is equal to the cost. So I said you might be expected to win €1.47, and as long as that game cost €1.47 to play, that would be a fair game. So some people would tend to think, oh, it's fair if I win money, it's not fair if I lose money. But in probability, we describe something as being fair if the expected value is equal to the cost. So that's what we're going to need to check to determine whether something is a fair game. So we have a couple of questions to look at here that are going to deal with expected value and fairness, and they just ask them in a couple of different ways. So there's a bit of work to them. So the first one here is 2018 paper 2 question 3 part B. So this says a game called Rainbow uses an unbiased circular spinner. The spinner has 7 sectors coloured red, orange, yellow, green, blue, indigo and violet as shown below. The table below also shows the angle of each sector. It also shows the cash prize that a player wins if the spinner stops in that sector. So we have this spinner and it's not equally divided. So it's not divided divided up into 7 equal segments, I can see that green is definitely a bigger segment than yellow, and so on when we're looking at this spinner. So when we have this question, the first thing that we're going to have to work out, it says complete the probability column in the table, which shows the probability of the spinner coming to rest in each sector after one spin. So we're going to have to calculate the probabilities here. So how we're going to do this is it tells us the angle of each of the colours, and all we're going to do is convert those angles into a fraction. So we're going to say, well, what is the probability of each of these? And why I'm going to use a fraction is that their example was a fraction. So we have a 1/8 probability here of getting a yellow because yellow is 45 degrees. So when they have one piece filled in for me, that's a guide to what way I should write my probability, because probabilities can be written as decimals or fractions or percentages, but in this question we're going to write them as fractions. So how we're going to calculate those probabilities is we're going to take our colour, we say the angle is 72 degrees, out of the total angle in a circle is 360 degrees. So when we take our calculator and say 72 degrees divided by 360 degrees, that gives us 1/5. So the probability of getting a red is 1/5. Out of this spinner here, 1/5 of it is landing on red, so the probability of getting red is 1/5. And we do that for each of these angles here as we go through them. So for orange, it works out to be 1/12, so that's 30 over 360. For green, it's 90 over 360, which is 1/4. For blue, it's 60 out of 360, which is 1/6. For indigo, it's 18 out of 360, which is 1/20th. And for 45 degrees, it's 1/8. So 45 out of 360 is 1/8. So now we've worked out the probability of getting each of those colours. And that was the first thing that it asked me to do, was to complete the probabilities. The second thing it asks us to do is find the expected value of the prize that a player wins if they play rainbow. So if we're going to play this game, how much money can we expect to get? So that's our expected value. Or what's the average payout or the average amount of money that people win when they play this game? So to work this out, we know that our expected value formula is equal to the sum of x multiplied by px. So x is our values and the probability of x we've just calculated. So what's the probability of each of those values? And we're going to multiply those. And then this big sigma here tells us to add them together, the sum of. So my outcome here was red. So that's what it says on my spinner, is that this sector is red, but that's not the x value that we're going to take because I can't multiply red by 1/5. What we're going to be using as our x's is our prize. So this is our x value. So what is our value? So this is that if it lands on red, we're going to win €20. And the probability of it landing on red, so the probability of winning that €20 is 1/5. So this column here is going to be my probability of x. So we're going to take each of those x's and multiply them by their probability. So I'm going to say 20 multiplied by 1/5 and add them together. Plus 60 multiplied by 1/12 plus 24 multiplied by 1/8 plus 8 multiplied by 1/4 plus 42 multiplied by 1/6 plus 90 multiplied by 1/20th plus 48 multiplied by 1/8. So we're taking each of our x's, each of our values, and we're multiplying them by the probability of that value. So that gives me 4 plus 5 plus 3 plus 2 plus 7 plus 4.5 plus 6, and when we add those together we get €31.50. So if we play this game we expect to get €31.50 back. Now €31.50 isn't one of our outcomes, so we saw 20, 60, 24, 8, 42, 90 and 48, and we're saying we expect to get €31.50, but that's absolutely fine. It's on average as we play this game, that is going to be our average payout. So that's an example of our expected value. It didn't ask us anything about fairness in that question. So we'll see in the next question that we're going to be given a part asking about fairness. So this is from the 2014 sample paper 2, and this is question 2. So it says a biased die is used in a game. The probabilities of getting the 6 different numbers on the die are shown in the table below. So when we're talking about a biased die, this means that it's not fair. So this die is definitely not a fair die. And we can see that it's not a fair die because we know that this is a cube die and we should have equal outcomes or equal probability of getting any of those outcomes. Now here we can see the probability of getting a 1 is 0.25, of getting a 2 is 0.25, of getting a 3 is 0.15, of getting a 4 is 0.15, of getting a 5 is 0.1, and of getting a 6 is 0.1. Now even when it's a biased die, the probabilities here have to add up to 1 because they're all the possible outcomes, and that will always be 1. So it says find the expected value of the random variable x, where x is the number thrown. So this time it's not about winning money at the moment, it's just what value do I expect to get on the die. So it's going to be the same thing where we're going to say the sum of xpx is equal to my expected value. So this time my value is 1 and the probability of getting that 1 is 0.25, plus my expected value is 2 and the probability of getting a 2 is 0.25. My value is 3, so my x is 3 and my probability of getting that 3 is 0.15. My value is 4, so that's my x, and my probability of getting that x is 0.15. My value is 5, and my probability of getting that 5 is 0.1. My value is 6, and my probability of getting that is also 0.1. And we're going to sum all of those together. So this is 0.25 plus 0.5 plus 0.45 plus 0.6 plus 0.5 plus 0.6. And when we sum all those together, we get 2.9. So when we roll this dice, because it's a biased die, we expect to get a value of 2.9. And again, we know that the outcomes on this die are 1, 2, 3, 4, 5, and 6. So we cannot get an outcome that is 2.9, but that is the average value or the expected value when we roll this biased die. Part B then turns this into a game. So it says there is a game at a fun fair. It costs €3 to play the game. The player rolls a die once and wins back the number of euros shown on the die. The sentence below describes the difference between using the above biased die and using a fair or unbiased die when playing this game. By doing the calculations required, complete the sentence. Okay, so we know that if we use this biased die that we had in part A, we would be winning back on average €2.90. So that's our expected value. So with the biased die, our expected value is equal to €2.90. And it tells us here that it costs €3 to play the game. So the cost of this is €3. So we can see that this is not a fair game. It costs us more than we expect to win back, so it's not fair. So we'd be saying, will we expect to lose 10 cents per game? So if you play the game many times with a fair die, you will win an average of, so we don't know this yet, per game. But if you play with the biased die, you will lose an average of 10 cents per game. So we've worked out what it is for our biased die. Now we're going to have to do the exact same thing with a fair die. So what we need to know with our fair die, what are our outcomes? And what is the probability of that outcome? So we know that we have a 1, a 2, a 3, a 4, a 5, and a 6. And on our fair die, each of those are equally likely to occur. So that's a 1/6. So to work out the expected value on our fair die, we're going to take our x value and multiply by the expected value of that. So 1 times 1/6, 2 times 1/6, 3 times 1/6, 4 times 1/6, 5 times 1/6, and 6 times 1/6. So when we had our biased die, our probabilities were given as decimals. When I have my fair die, I'm going to use fractions. Just because 1/6 doesn't turn into a neat fraction for me, I'd have to do rounding, or I'm going to have a recurring decimal. So I'm going to leave them as fractions. And when we do that, we get an average of 3.5. So when I would roll a fair die, I would expect to get a value of 3.5. And because we're now dealing with money, so we're saying if we roll a 1, we get back €1. If we roll a 6, we get back €6. We're now going to say that that's €3.50 for our fair die. So our expected value for our fair die is €3.50, and it still costs €3. So it's still not a fair game. So now that we have our fair die or our unbiased die, it's still not a fair game because the game costs €3, but we would expect to be winning €3.50. So the cost is not equal to the expected value, so it's still not fair. So this time we're going to say, well, we expect to win €3.50 and it costs €3. So this time we're expecting to win an average of 50 cents per game. So that's how we deal with expected value and how we look at whether things are fair or not. The second thing that we're going to look at in this lesson is something called Bernoulli Trials. And when we're looking at Bernoulli Trials, these are named after a person, and a Bernoulli trial is how we carry out a probability when there's going to be a certain number of conditions. So for a Bernoulli trial, there can only be 2 outcomes. And we call them success and failure. So we can only have these 2 outcomes. They have to be success and failure. So what that means is if I was saying flipping a coin and I wanted to know the probability of heads, then I can say head is a success and tail is a failure. If I was rolling a dice and I could say an even number is a success and an odd number is a failure because they're the only 2 things. But I couldn't say rolling a 1 or rolling a 2 or rolling a 3 because they're 3 different things, so I can't have just 2 outcomes. But you can have rolling a 1 or not rolling a 1. So when we're looking at Bernoulli trials, we always have to look at things as being only 2 possible outcomes, success and failure. We also have to have a limited number of trials. So that means that we're going to be told a die is rolled 7 times or a person tries something 10 times. So we're going to have a certain number of trials when we're carrying this out. And really important is that the outcomes need to be independent. So if we have independent events, what that means is that the probability doesn't rely on something happening already. So it means that the probability isn't going to change as we go through this experiment. So you might know from real life that you might be, okay, this person taking a penalty, if he or she misses the first penalty, they become more likely to miss the second penalty, more likely to miss the third penalty, because what's happened already in the game is going to affect them. But when we're looking at Bernoulli trials, we're saying this is the probability that they're going to score, and that remains constant each time. So it doesn't matter what has happened before, that we're going to have our independent events that we're going to have no effect on our probabilities as we go through them. And this is going to be dealing with our and. So we're going to see this and this and this happening. And when we're dealing with and in probability, we know that we're going to be multiplying probabilities. So we're going to see this and this happens. So what is that probability? So to look at a question that goes with this, 2014 paper 2 question 2, this says when taking a penalty kick, the probability that Kevin scores is always 3/4. So it never changes. It's always 3/4. It doesn't matter what has happened already in this game. The probability that he's going to score is 3/4. Kevin takes a penalty. What is the probability that he does not score? So there's only two possible outcomes here. We either score this penalty or he doesn't score this penalty. So that means they're the only two possible outcomes. So the probabilities of success and failure have to sum up to 1. So the probability that he doesn't score will be 1 minus 3/4. So that means that if there's a probability that he's going to score is 3/4, the probability that he won't score is going to be 1/4. And that's going to be the same each time. So we have our success of scoring a penalty of 3/4 and our failure of not scoring a penalty is 1/4. So then we're told Kevin takes 2 penalties. So this is, we have our definite number of trials. He's scoring 2 penalties and we're being asked to calculate what is the probability that he scores both. So we're looking for the probability that he scores and scores. So when we see this word and here, that's telling us that we're going to be multiplying our probability. So we're going to say the probability that he scores the first one, that's 3/4, because it's always a probability of 3/4 that he scores. And so multiply by the probability he scores the next one is 3/4 as well. So we multiply these two fractions and that gives us 9/16. So the probability that he scores both of these penalties is 9/16. In the last part, the part C of this, Kevin takes 3 penalties. So again, we have a definite number of penalties. What is the probability that he scores exactly twice? So we're going to say he scores exactly twice. That can happen in a couple of different ways. So if he's going to score exactly twice, he can score, and not score. Or he could not score, and score. Or he could score, not score, and score. So they're the 3 different ways that this can happen. So we can see that there's 3 different ways of this happening. So I'm saying it's this, or this, or this. And we've already seen with our probability that when we say or, that tells us to add our probabilities. So we can work out our probability of score, and not score. So the probability that he scores is 3/4. And so multiplied by, he scores again, so that's another 3/4. And so multiplied by, he doesn't score, so that's going to be 1/4. So 3/4 by 3/4 by 1/4, that's going to give us 9/64. Now we can do exactly the same for the other 2 ways. So we can say the probability of not score, and the probability of score, not score, score. But they're going to be exactly the same fractions. So for example, for the last one, score and not score and score. And that's also going to give us 9/64. So what we can do is we can say it's 9/64 plus 9/64 for this one as well, plus 9/64 for the last one. So because we're saying or, we're going to add together those probabilities. So 9/64 plus 9/64 plus 9/64. And that's going to give us 27/64. So the probability that he scores exactly twice is 27/64. We could also just say the probability for one of these examples is 9 over 64, and all three of them is going to be the same. So we could say just take that 9 over 64 and multiply it by 3, and that will still give us the same answer of 27 over 64. Okay, so how did we know that we needed to use a Bernoulli trial there? We were told that the probability that he always scores is always this value, so it's not going to change. The only other thing that can happen is that he does not score. So we're told what's the probability he does not score. And then we're given a definite number of trials. So he scores 2, or he takes 2 penalties, and then he takes 3 penalties. So we're going to use our Bernoulli trial with them. The last part says Kevin takes 5 penalties. What is the probability that he scores for the first time on his 5th penalty? Right, so this is another way that we know we're going to be using a Bernoulli trial. So when they say, what is the probability that this time happens on this turn? That's another example of a Bernoulli trial. So if he's going to score for the first time on his 5th penalty, that means he has not scored the first one. He has not scored the second one. He has not scored the third one. Not scored the fourth one, and then he scores the last one. So not score is a quarter, 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 and score is 3/4. And it's this and this and this and this. So we're multiplying them, and that gives us 3 over 1024. So the probability that he scores for the first time on his 5th penalty is 3 out of 1024. And again, we had a definite number of trials, 5 penalties, so we knew we were dealing with a Bernoulli trial. Another way that they can ask this that we have to work out, this is also going to be a Bernoulli trial, is 2020 paper 2 question 1 part B. So it says, in a large population, 1 in 8 of the people play tennis. 4 people are chosen at random from the population. What is the probability that the 4th person chosen is the only one to play tennis? This is very similar to that last question where we were looking at there with Kevin taking his penalties, but it doesn't break it down for us as much. So what we're going to look at here is the probability that a person plays tennis is 1 out of every 8 players, or every 8 people. So that's 1/8. So then the probability of not tennis is 1 minus that 1/8, or the 7 other people out of those 8 people that don't play tennis. So 4 people are chosen at random from the population, so we have a definite number of trials. What is the probability that the 4th person chosen is the only one to play tennis? So that means the first person doesn't play tennis, the second person doesn't play tennis, the third person doesn't play tennis, and the last person does. So the probability of not tennis is 7/8, not tennis is 7/8, not tennis is 7/8, and tennis is 1/8. And when we put that into our calculator, we get 343 over 4,096. So the probability that the 4th person chosen is the only one to play tennis is 343 over 4,096. The last part of this question then says 3 people are chosen at random from the population. So we have a definite number again. So this time we have 3 people. What is the probability that exactly 2 of them play tennis? So this is again, like we had with Kevin, we need to write down all our possibilities. So exactly 2 of them play tennis. So it could be tennis, tennis, not tennis, or tennis, not tennis, tennis, or not tennis, tennis, tennis. So we can see that there are 3 different ways of doing this as well. So we're going to get the same fraction each time, and we can say this or this or this, so we can add them together, or we can work out one fraction and multiply it by 3. So the probability of tennis, tennis, not tennis would be 1/8 by 1/8 by 7/8. And that's going to give me 7 over 512. And then we have 3 different ways. So we take that fraction and multiply it by 3, and that gives us 21 out of 512. So the probability exactly to play tennis out of these 3 people is 21 out of 512. Okay, so that lesson is going through our expected values and how we show if something is a fair game. And it also goes through our Bernoulli Trials. And remember one of those videos there, so the 2019 paper 2 question 3 is going to be about Bernoulli Trials. And the other video there in the chat is a probability question from 2017 paper 2 question 1. Thanks.